Hello, my name is Carlo Silvestri. I'm a PhD candidate of the 34 cycle, and the title of my project is Numerical Study of Quantum Cascade Laser Dynamics. My supervisors are Mariangela Giannini, Lorenzo Columbo, and Massimo Brambilla from Politecnico di Bari. Quantum cascade lasers are semiconductor lasers, and they are unipolar devices since electronic transition occur between confined states in the conduction band, so holes are not involved. And the emission spectral regions of quantum cascade lasers are mid-infrared and terahertz. First topic that I work on is the generation of optical frequency combs by using quantum cascade lasers, and two main applications of this study are spectroscopy, in particular dual comb spectroscopy, and also applications in the optical communication area. The second topic is the self-detection scattering snow, which is a technique which combines self-mixing interferometry and scattering type near-field optical microscopy, and it is used for retrieving dielectric properties of material resonant in the terahertz and also for imaging at high resolution. Now let's consider adopted methodologies. In order to study optical frequency combs in quantum cascade laser, we derived and simulated the effective semiconductor Maxwell block equations. In the previous part of my work, I studied the Fabry-Perot configuration. In the last part of my research, I studied the ring configuration, and I'm going to show the results related to the ring configuration. The set of equations related to the ring configuration is shown on the right part of this slide. In the study of self-detection scattering snow, we exploit the Lanko-Bayashi model, which describes the dynamics of the laser in presence of optical feedback, and in particular we use the steady-state solutions of this model. Let's consider now novel contributions and results. Let's consider the results related to the simulation of effective semiconductor Maxwell block equation for the ring configuration. In this slide, we show a bias current sweeping, so by fixing line width enhancement factor and gain dispersion bandwidth, and we plot by varying the current the main indicator that we use to recognize the locked regime. And we can see that also in this case, as we had for Fabry-Perot configuration, we have an alternance between locked and unlocked states, but in this case, in absence of special hole burning. We have less locked modes in the -10 dB band with respect to Fabry-Perot, and also the lock regimes are not characterized by the presence of linear chirp. This is an example of lock regime. We can see that the output powers is characterized by structures, but these structures are not sitting on constant background as it happened in the Fabry-Perot. Also, the instantaneous frequency is not characterized by linear chirp, and this lock regime, they satisfy the definition of harmonic frequency combs. So we obtain some harmonic frequency combs in the case of the ring configuration. Furthermore, also we studied the ring configuration with optical injection. This is the on the left part of the slide we can find the theoretical model, and with the proper boundary condition in which it's inserted the injected field, and by integrating this model we could obtain some particular type of optical frequency comb like Turing rolls or cavity solitons. About SNOME, by using our simulator we reproduced experimental fringes provided by the Istituto of Nanoscienze CNR of Pisa, led by Miriam Vitiello, and we reproduced different set of fringes for two values of the frequency in two different conditions. First, for different values of the bias current, they are shown on the left of the slide, and then also we reproduce some fringes measured with different transmissions of the attenuator. The future work involves the study of direct modulation of the quantum cascade laser by achieving an increase of the extension of the comb regime and bandwidth, and also the simulation of a reduced model for Fabry-Perot configuration in both free running and in presence of optical injection.